All right, Calc, this is section 4.2. Um, 4.1 is always a sucky section, but 4.2 hopefully will be a little bit better for you. It should be. Um, there are, when you're finding derivatives, it's basically just like really, really basic algebra. And there are four main rules to finding derivatives. Um, this section we're talking mostly about the power rule. They also introduce in there the constant rule, but I think the constant rule kind of follows under the power rule. So I just lump this all into the power rule, and that's what we're learning in section 4.2. So these are rules of finding the derivatives without using the slope formula, all that nasty stuff that we had yesterday. Okay, so the first thing, constant rule. If you're taking the derivative of a constant like c, maybe this is the number 7, I don't know, like in example 1, maybe that's the number 32. If you're taking the derivative of any constant, the answer is 0. The derivative is always going to be 0. Okay, they use this notation to talk about derivatives. This basically means the derivative with respect to x. Okay, later on we'll be taking derivatives of x's and y's at the same time here in like coming chapters, but this means derivative with respect to x. Don't worry about this notation too much, but just remember that the derivative of a constant number is 0. So the derivative of 7 is 0, the derivative of 0 is 0, the derivative of negative 3 is 0, the derivative of k pi to the second power, when k is a constant and not a variable, is 0. Okay, and the reason why that is if we think about y equals 7 as a line, 1, 2, 3, 4, 5, 6, 7, it is this straight line here. So if we're looking at any point on this line and I'm looking at like that instantaneous slope on any of those lines, the slope, or the derivative, the slope of the tangent line, the slope at any one of those points is going to be 0. It's going to have 0 slope because it's a horizontal line. So slope of any constant number or constant value is 0. Okay. Now the power rule, there's a formula for it. You won't necessarily need to memorize this formula because you'll already know it after doing it so many times. Okay. So when you're taking the derivative of x to the third power, okay, the power is going to be your value of n. Okay. What you're doing is you're taking that n, you're putting it down in front, and then you're subtracting 1 from n, and that becomes your new exponent. Okay, so x to the third power. I take that 3, I drop it down in front, and I subtract 1 from 3. 3 minus 1 is 2. So the derivative of x to the third power is 3x squared. Done. That's it. Okay. Now, I'm going to do number 3 before we do number 2, because 2 is a little bit tougher. Number 3, 1 over x squared. Okay. I want to be able to deal with the x when it's in the numerator. So I have to bump him up to the numerator, even though it makes him uglier. If I bump him up to the numerator, he will become x to the negative 2 power. And this is actually easier to find the derivative than this guy. Okay, so negative 2, I drop him down in front, and then I subtract 1 from the exponent. Negative 2 minus 1 is negative 3. Okay, so this is the new derivative. And then I want to rewrite him so he's nicer again. And I'm going to bump him back down to the denominator to make him a positive, or x to the positive third power. So he will look like that. Negative 2 will stay in the top, and x to the third power will go back down to the bottom, and that's what his derivative will look like. Okay, so even though his exponent became negative, he was still okay. He was nice to deal with. All right. Number 2 is a little bit tougher. You have to kind of really have a good knowledge or good background of exponents to be able to do some of these derivative rules. All right. So the cubic root of x, you're going to want to remember how to simplify like cubic roots. X to the 1/3 power is the same thing as the cubic root of x. Remember that. Anytime you have a root, it becomes a fractional exponent. So remember that. All right, so I want to take the derivative of x to the 1/3 power. So I'm going to move the 1/3 down in front. I leave the x, and then I'm going to subtract 1 from the exponent. So 1/3 minus 1 is going to be now to the negative 2/3 power. Negative 2/3 power. Okay. Now, just like we did over here in this example, I want to make that a positive 2/3 power, so I'm going to bump him down to the bottom. he is now going to be joined with the 3. And since he's down at the bottom, he will now be positive 2/3 power. Okay. If you leave your answer like that, I'll probably say that that's okay. But if we want to make that a little bit more simplified, 2/3 power means the cubic root of x squared. That's what 2/3 power means. Okay. And that is my final derivative. So a little bit trickier than what this one or even example 1 was. But you really just have to know how exponents work. Okay, as long as you can figure your exponents out, these rules are very easy. All right, now, examples 1, 2, and 3, we're all finding derivatives, slopes of tangent lines, okay? But 3x squared is not a slope, okay? So how does that make sense, right? A slope is just a number. Well, it's not a slope until I plug a point in, all right? If I'm looking at the equation of x to the 3rd power, I'm looking at the graph of x to the 3rd power, I need to find the derivative of, or the slope of the tangent line, but they have to tell me what point I'm looking at or what place on the graph I'm looking at before I can find that exact slope, okay? We're going to illustrate that down here in this example. So I'm starting with x to the 4th power, which I've lied to you up until this point. X to the 4th power just by itself is not a w, it's just kind of a flat tire, okay? It looks like a parabola, but it's a little bit flatter in the middle. So we're wanting to know what the slope of the tangent line is at -1, what this guy's slope is, at 0, what this guy's slope is, and at 1, what this guy's slope is. Okay, we want to find each one of those slopes. So in order to do that, I take the derivative of x to the 4th, which is 4x to the 3rd. Drop the 4 down in front, subtract 1 from the exponent, 4x to the 3rd. That's going to give me the slope of my tangent line, but I have to plug the point in before it will give me the numerical slope. So 4 times -1 to the 3rd power will be -4. This line right here has a slope of -4. Okay, let's look at 0. 4 times 0 to the 3rd power is just 0. This guy has a slope of 0. 1, if I plug 1 in, 4 times 1 to the 3rd power is just 4. So this guy has a slope of 4. Okay, so yes, 4x to the 3rd power is not a slope. It's still a derivative. This will give me the slope if I plug any particular point in. Okay. Now, next example, find the equation of a tangent line. Now we don't want just the slope. I want the equation of the whole line, and lines are of the form y equals mx plus b. So I don't just want m, I want the equation of the whole line. All right. So just like up here, we're going to find m, but then we have to finish it out and find the entire y equals mx plus b, right? So tangent line to the graph of x squared, all right? So x squared, if I think about what he looks like, you don't have to graph these every time. I'm just doing this so that you can see. That's what my parabola looks like, y equals x squared. Okay, I want to know at -2 what the equation of that line is. Okay, I know he's going to have a negative slope, but we want to figure out what the entire equation is. So I'm going to take the derivative of x squared, which is 2x to the 1st power. I drop the 2 down in front, subtract 1 from the exponent. And now I'm going to plug -2 in because that's the point that I'm looking at. Right? So 2 times -2 to the 1st power is -4. So my slope is -4. I'm going to plug that in here. Y equals -4x plus b. And now I just have to find b. Okay? We've done problems like this before, like way back in like chapter P, where you're trying to write a linear function. To find b, you have to plug something in for x and something in for y. Well, I have something to plug in for x, but I don't have something to plug in for y. So we need to figure out what y I can plug in, all right? If I think about where -2 lives on the graph, he's right here. -2 is on the graph of my parabola, and I need to find the y-coordinate of that -2. So -2 comma what? What is the y-coordinate? Well, to figure out that y-coordinate, I can plug it back into the original function. -2 on this graph will hit at +4. I plug -2 into the original function, it will hit at +4. So this point right here is at -2, 4. Those are going to be the values I'm going to use to plug in for x and y. Okay, so 4 is equal to -4 times -2 is +8. plus b. And then I'm going to subtract 8 from both sides, and b is going to be negative 4. So I write that all together as y equals negative 4x minus 4. And there is the equation of my tangent line. Not just the slope of the tangent line. The slope is negative 4. I want the entire equation of the line. Okay? All right, I'm going to go down here and start into one of these problems before I introduce the constant multiple rule to you. So looking at 2 over x, we want to rewrite that so that I'm able to find the derivative. And I want to bump this x up to the top. Right now this is x to the first power, so when I bump him up to the top, he will become 2x to the negative first power. Okay, now I find the derivative. The derivative, when I'm doing this, says, or the constant multiple rule says that if I have a constant in front of my x, like 2, it's okay. All I do with my exponent when I bring it down is I multiply it. So I can have numbers out in front of here. Just when I bring that negative 1 down, I'm just going to multiply it by the constant that's out in front. So when I bring my negative 1 down, negative 1 times 2 is negative 2x, and I subtract 1 from here. So that will give me negative 2x to the negative 2 power, right? If I simplify that, I want to move him back down to the bottom so that he becomes positive again. So I can have negative 2 over x to the positive 2, and that is simplified. That is my derivative. Okay, looking at the second one, number 2. Okay, this one's going to take a little bit more writing because I want to rewrite that cubic root of x squared a little bit. Okay, so this 1/2, I'm going to leave him alone, 1/2, and I'm going to write x, the cubic root of x squared, as x to the 2/3 power. That's what the cubic root of x squared is. X to the 2/3 power. We had that up here. X to the 2/3 power is the cubic root of x squared. All right. So now, in order to deal with him, I'm going to move him up to the top. Okay, I have to have him in the numerator. And I'm really going to kind of separate him from this 1/2. So I'm going to drop the 1/2 off to the side, and if I bring the 2/3 power up, the x to the negative 2/3 power up, it will become negative. Okay, so just bringing that 1/2 and separating that 1/2 and bringing this guy to the top will become negative 2/3 power. Okay, now I can do my derivative. So I want to bring the negative 2/3 down in front. So that looks like 1/2 times negative 2/3. I'm going to multiply those two together. I can cross out my 2's, so that will become negative 1/3 x. And if I subtract 1 from negative 2/3, you guys are going to get good at these because you'll be doing this a lot. Negative 2/3 minus 1 will be like negative 2/3 minus 3 over 3. So negative 5/3, just like that. Okay. I want this exponent to become positive again, so I'm going to lump him back down under with the 3. X to the positive 5/3. Okay, now he's back down in the bottom again. And then I can write that as the cubic root of x to the 5th power, I think is what that will look like. Okay, so 5/3 power is cubic root x to the 5th power. All right, I'll do one more of these. I'll do number 3. Okay, because I'm in another room. Example 4 is very similar to that. So let's do number 3. This 3rd power in the bottom has to be distributed. So I'm going to do that first. Let's rewrite him. 2 to the 3rd power is 8. And x to the 3rd power is just going to become like that. So by simplifying and getting rid of those parentheses, he looks like this. Okay, I'm going to detach him again from the 5/8 like I did up here with the 1/2. Detach him from the 5/8, and the x to the 3rd power is going to move up to the top. So he will look like 5/8 x to the negative 3rd power. Okay, now I can do my derivative. I multiply by negative 3. I drop the negative 3 down in front. So that is like 5/8 times negative 3 over 1. Oh my goodness, that will be like negative 15 over 8. Okay, it's ugly, but leave it. And I subtract 1 from the exponent, negative 4. Okay, Now I'm going to move him back down underneath. So negative 15 over 8 x to the fourth power. And that's what he will look like. Okay? Kind of ugly, but that's what the derivative is. All right? One more thing on the backside. Oops. I don't have a backside. You do. Let's go over these examples, and then we'll talk about rates of change when I come back on Thursday. So the sum and difference rules, I notice a typo here. For some reason, copy-paste, I just copy-paste it. This is the sum rule. The difference should have minus in it, so this should be a negative symbol. This should be a negative symbol. Okay? Sum and difference rules, all this means is that if I have pieces, like 3 pieces here, you're just going to take the derivative of each piece individually. It's like, if this is f of x and this is g of x, I just take the derivative of each piece individually, right? So the derivative of x to the third power, I drop the 3 down in front, subtract 1 from the exponent, okay? Now the derivative of negative 4x, this is like x to the first power, okay? Derivative of negative 4x, I drop the 1 down in front. Negative 4 times 1 is still just negative 4. And now I have x to the 0 power, right? X to the 0 power is just 1, so basically like goes away. And then the derivative of 5, our very first rule says if you're taking the derivative of a constant, it's 0. So he basically just goes away. So my derivative is 3x squared minus 4, right? Over here, at number 2, I'm just going to take the derivative of each piece individually, okay? I don't like the way that this first number is written, so I'm going to write him as negative 1/2 x to the fourth power. I separate the number with the variable, okay? So to take this derivative, I drop the 4 down in front. There's already a negative 1/2 there, so I'm going to multiply. Negative 1/2 times 4 is going to be negative 2 x to the third power. I subtract the exponent. So 4 times negative 1/2 is negative 2 x to the third power, plus, take the 3, drop it down in front. There's already a 3 there. 3 times 3 is 9 x, subtract 1 from the 3, and that's 2. Okay? There's a 1 exponent here. 1 times negative 2, subtract 1 from the exponent, it is 0. Okay? You'll notice that anytime you have like x to the first power, like over here, x to the first power, when you take the derivative of that, it's just the constant that's out in front, because the x to the first power will end up becoming x to the 0 and it will go away. Like over here, x to the first power ended up just dropping off and your constant is just negative 2. And that's all that I have, okay? So when you have multiple pieces, all you have to do is take the derivative of each piece individually and you are good to go, okay? I went ahead and posted homework up on the Google Classroom page, so make sure that you are working on that. And we'll talk about velocities and rates of change when I come back on Thursday. Okay?